Okay, so part two. So we've got our assembled global stiffness matrix and the right hand side body vector. Now let's see how we can find the element wise stiffness matrix and the right hand side body vector. So basically let me jump to that. लेकिन उसके लिए I'm just going to put all the information that I need on one slide ताकि it makes it easy for me to start with this problem. So I have my two elements. उनकी ये nodal positions हैं. Finite element equations ये रही सारी की सारी, right? Where the element wise stiffness matrix, for example, is given by this expression. And then the individual expressions for my shape functions are given by these right here. ये Hermitian shape functions हो गए. So of course there will be a k for element 1 and a k for element 2 and a b body term for element 1 and for element 2. So this is quite an involved process, so I'm not going to go into finding all of these. Instead, I'm just going to use the element stiffness matrix for element 1 as an example. So I'm looking at trying to find k1. So k1 के लिए I'm looking at this expression right here. ठीक है जी. So इसके अंदर I can see I have my B matrix. B matrix के अंदर क्या है? I have my double derivatives of the shape functions. So I need my shape functions primarily then, right? So shape functions क्या हैं? वो they're given by these expressions right here. So a good starting point then, not just a good starting point, the only starting point that we have is that we should start by finding our shape functions for element 1 first. Okay, so how do we do that? We look at let's say हम n1 से शुरू करते हैं. तो clearly n1 के अगर हम expression को देखें, then all it has is the nodal positions. ये देखें ये x2, ये x1. So the nodal position of the position of node 1, the position of node 2, and L, the length of the element. So this is the only these are the only pieces of information that I need to find n1, and all I need to do is substitute those values into this expression. So अगर मैं n1 के लिए ये करूँ, then I get okay x minus x2. x2 क्या है? x2 is 5. So x minus 5 whole squared, bracket close and bracket next wala open, minus L. L is the length of the element, which is 5, plus 2 times x1. x1 क्या है? 0. So that just disappears. Minus x. So minus x. All of this divided by L cubed, which is of course 5. So 5 cubed. Great. So simple, straightforward substitution of the element nodal positions and the element length. Okay. And if I simplify this further, I get this expression right here. Similarly, if now let's look at M1. M1 के अंदर भी I have my nodal positions x1, x2 and L. So again, I just need to substitute those in here. So x minus x1. What is x1? x1 is 0, so it just turns into an x, multiplied by x minus x2. x2 क्या है? x2 is 5, so just x minus 5 whole squared, divided by let me just circle these कि ये nodal positions हैं x1 और x2 की, divided by 5 squared, so 25. Straightforward, just substitution into the expressions. इसी तरह हम अपने n2 और m2 को भी फाइंड करेंगे. सिंपल अगेन x1 और x2 की वैल्यूज जो हैं वो हमने अंदर सब्स्टिट्यूट कर देनी है, सो दैट आई गेट दीज एक्सप्रेशंस राइट हियर. प्लीज़, आई नो कि आई एम जस्ट गोइंग थ्रू दिस अ लिटिल बिट क्विकली, लेकिन आई वांट के you see the procedure first and then just do this example yourself. The only way to understand this completely is to practice yourself. So you must just practice and then use the slides just as a check कि आप लोगों की solutions ठीक है या नहीं. It may be कि मैंने कोई गलती की हो, तो please do this yourself and then let me know in case I've made a mistake. Anyway, okay, so I've got my shape functions, and then from my shape functions I can write out my n matrix if I so want. Just putting in the values for each of the respective n1, m1, n2, m2. ठीक है जी. अब अगर ये आ गया है तो फिर I can find my B matrix. B matrix किस तरह निकलेगा? It has the double differentials of the shape functions. So इस हर एक एक्सप्रेशन को लें और इसको डबली डिफरेंशिएट करें. So this is n1 right here. So n1 की पहली डिफरेंशिएशन then is just shown right here. Differentiate it again to get the double derivative. Similarly for each of the other shape functions to finally get our B matrix. ठीक है जी. और B matrix के अंदर be very careful. B matrix के अंदर double derivatives हैं. Okay. So all of these go into the B matrix. Great. And now that I have my B matrix, then I can write down what my stiffness matrix is, remembering what was KE? KE was, sorry, this may take me a little while, the integral of B E transpose EI times BE again, right? So अब इसको ज़रा गौर से सोचें. This is not a straightforward thing. So पहले तो let's think about कि हमारा K matrix का rank क्या था. So per node I have 2 degrees of freedom and each element has 2 nodes. So a total of 4 degrees of freedom per element. So my K matrix for the element is actually a 4 by 4. Next, let's just make sure that all of this also simplifies correctly to be a 4 by 4. So clearly B matrix mera kya hua hai? This is a row vector, right? Row vector with a rank of 1 by 4. So iska transpose would then be a column vector with a rank of 4 by 1. So indeed इनका ये 1 और 1 cancel होके they do give me a 4 by 4 product, right? और फिर उसका integral. So something which is actually pretty complicated. So if I expand this out and write them, पहले simple again, वही matrix form में लिख कर उसके बाद उनका product लिया. Then I think I will have to remove जो यहाँ पे लिखा हुआ है. Then I get this KE matrix right here, which is essentially consists of some particular terms of the B matrix being multiplied by some other one. So for example, K11 ke andar would be B1 ka squared, 12x minus 30 divided by 125 whole squared. And then K12 may instead I would have B2 multiplied by B1, which is exactly what I have, and so on and so forth. Again, ये इस तरह directly हम नहीं लिख सकते. आपको वही K matrix की expression को लिख के B's को लिख के expand करना होगा, which I had done right before. ठीक है, वो column vector की multiplication with the row vector लिख कर और फिर उनका integral. Okay, do not try to skip steps. Do this out because of lack of a board, इसलिए we are having to do it this way. Okay, so ठीक है. So if I do this matrix multiplication, then this is what I would end up getting. And then notice कि ये इतनी बड़ी सारी matrix को I have to integrate each of the terms within this 4 by 4 matrix. Thankfully it is symmetric. So थोड़ा सा हमारे लिए काम आसान हो जाएगा, लेकिन still it's not that straightforward and requires quite a lot of computation. So I'm going to skip this step and hopefully you are beginning to see why even एक simple किस्म की beam bending problem को solve करने के लिए भी manually कितने ज़्यादा steps required हैं. Okay, which is why a computer would be really really helpful. Okay, so I'm going to give you the solution and I invite कि please आप लोग खुद try करें इसकी integration करने का to see that it just so turns out that the K matrix the stiffness matrix for both element 1 and 2 turns out to be this matrix right here. For both of them, please note, ये मैंने खुद करके फिर I've just summarized it, ठीक है? But you should try it for both the elements. Okay, so the K matrix turns out to be this, and the body vector for both of the elements again also turns out to be the same and is equal to this expression right here. ठीक है जी, नोट के बी बॉडी फाइंड करने के लिए आई वुड हैव यूज्ड दिस एक्सप्रेशन राइट हियर, ठीक है, which would have the integral of the shape functions. Okay, so now that we have our element-wise stiffness matrix and element-wise body term, I can assemble them using our slide 7. So assembling them together, I can write down my global stiffness matrix, K, and my global body term like so. ठीक है जी, तो ये मैंने वही हमने स्लाइड 7 पे जो असेंबली का एनालिसिस किया था उसके अंदर सब्स्टिट्यूट कर दिया है. जस्ट नोटिंग, पहले भी हमने ये बात नोट की थी कि हमें पता है कि इट्स ओनली द 3-4 टर्म्स जहाँ पे कुछ इफेक्ट हो रहा है, सो उन्हीं के ऊपर दोनों के दोनों एलिमेंट्स कंट्रीब्यूट कर रहे हैं. ओके, so अब I've got my global stiffness matrix, I've got my global right hand side body vector. So please be careful, body vector आया, मेरे पास right hand side vector नहीं आ गया. तो right hand side, global right hand side vector को find करने के लिए I also need to add in the effect of the point loads, or we'll come to the point loads in just a second. Okay, so once we've got all of this, let's start to write all of this down for our global matrix equation को. लेकिन उससे पहले वो करने के लिए हमें अपनी बाउंड्री कंडीशंस की तरफ भी जाना होगा. तो हमारी ग्लोबल इक्वेशन ये है पूरी की पूरी. We've already got our K, I've got my K, I've got my B omega, I still need my A, and I still need my B point. Okay, so first let's see कि A के अंदर क्या है. Of course this contains the nodal degrees of freedom, so I need to look at then my essential boundary conditions. So if I'm looking at my essential boundary conditions, I can see that मेरे जो nodes थे, let me draw those in as well. I had a node right here, and a node right here, and a node right here. So I can see कि मेरे node 1 के ऊपर तो it's completely clamped, fixed support है, which means a fixed support basically implies that both the deflection and the rotation here are 0. That's what a fixed support does. वो ना deflection होने देता है और ना कोई rotation होने देता है. So that means कि मेरा V1 and theta 1 दोनों 0 हैं. Next, node 2 के ऊपर एक roller support है. अब roller support जो है ना, वो सिर्फ और सिर्फ डिफ्लेक्शन होना प्रिवेंट कर देता है. वो इसको इससे नीचे नहीं जाने देगा, और बिकॉज ऑफ द डायरेक्शन ऑफ द रोड वी आर ओनली इंटरेस्टेड इन डिफ्लेक्शन इन दिस डायरेक्शन. So it prevents any deflections, this roller support right here, but rotations वो allow करता है. Beam can rotate whatever it wants to. Okay, so only V2 is 0 because of this roller support. ठीक है, so you need to be a bit careful कि fixed support का क्या effect होता है, roller support का क्या effect होता है. Okay, so those are, and that's it. यही हमारी essential boundary conditions है. Then moving from our essential boundary conditions, तो ये हम इससे हमें हमारा A मिल जाएगा. Then let's move on to B point. See, so for the point loads, I need to look at my natural boundary conditions. So natural boundary conditions को analyze करने के लिए what I need to do is to think about the fact कि कहाँ कहाँ पे मेरे पास point loads apply हो रहे हैं. सो क्लियरली ये नोड 3 के ऊपर तो कोई पॉइंट लोड नहीं है, वो फ्री हैंड है, कुछ ना फोर्स लग रही है ना मोमेंट लग रही है. नोड 2 के ऊपर अलबत्ता कुछ ना कुछ ये जो रोलर है ये कोई सपोर्ट रिएक्शन प्रोवाइड करेगा, और ऑल्सो नोड 1 के ऊपर भी ये फिक्स सपोर्ट भी कोई सपोर्ट रिएक्शन, पॉइंट सपोर्ट रिएक्शन अप्लाई करेगा. सो हाउ वी थिंक अबाउट दैट इज़ दैट वी नीड टू रिमेंबर कि जहाँ पे मेरे पास डिफ्लेक्शन ज़ीरो हो रही है या जहाँ पे मेरे पास डिफ्लेक्शन प्रिस्क्राइब हो रही है, वहाँ पे force unknown होगी, right? Wherever there is a known vi, then there will be an unknown force there. ठीक, तो अगर मेरे पास v1 0 था, then that means कि मेरे पास यहाँ पे कोई unknown point force apply हो रहा है. Let me call that q1. और अगर मेरे पास θ1 0 था, that is wherever I have a known theta boundary condition, then I will have an unknown moment there. That is, अगर यहाँ पे θ1 0 है, then I also have an unknown moment m1. और इस unknown moment को मैंने अपनी positive sign convention के हिसाब से draw किया है as being anti-clockwise positive for the beam. ओके, लास्टली रिकॉल के V2 के ऊपर, सॉरी नोड 2 के ऊपर डिफ्लेक्शन ज़ीरो थी, तो अगर डिफ्लेक्शन ज़ीरो है दैट मीन्स कि उधर आई हैव एन अननोन फोर्स एक्टिंग. आई एम गोइंग टू कॉल इट Q2. Okay, so those are my point loads and they basically give me my B point. Okay, now I can assemble, or just to be sure, there are no other point loads acting apart from these reaction forces and moment. So yes, so I've got my B point now. So basically now I've got all the things I need from my global finite element equation and I can write it all down. Okay, so write it all down. This is my global K matrix. This is my A vector. नोट के मुझे ये बाउंड्री कंडीशंस पता थी, v1 θ1 v2 0 है, तो ये पहली तीन टर्म ज़ीरो हो गई, बाकी तीनों अननोन है. देन आई हैव माय b ओमेगा, दैट इज़ माय राइट हैंड साइड बॉडी वेक्टर जो मैंने असेंबल किया था यूजिंग द एलिमेंट वंस, एंड देन प्लस द b पॉइंट. और b पॉइंट के अंदर आई ओनली हैव पॉइंट लोड्स एट नोड 1 एंड एट नोड 2, और नोड 1 पे फोर्स और मोमेंट दोनों हैं और नोड 2 पे सिर्फ फोर्स है और बाकी सब कुछ फिर ज़ीरो होगा. ओके, नाउ ये आई होप के दिस इज़ ऑल क्लियर. So now I can start to manipulate this equation, matrix equation, noting के हम लोग वही manipulation का वही पुराना procedure which we've already gone into in detail, कि जहाँ पे मेरे पास मेरी essential boundary conditions होती हैं, उन rows को मैं पूरा का पूरा ज़ीरो करके eliminate कर दूँगी initially, और वो जब rows eliminate होंगी तो साथ ही ये वाले columns को मैं left hand side पे ले जाऊँगी. Now for this problem, now this is very important, only because for this problem मेरी essential boundary conditions already ज़ीरो थी, इसकी वजह से ये वाले columns पूरे के पूरे eliminate ही हो जाएंगे. Otherwise, please do look at, I think it was lecture 5 या lecture 4, please do go back and look at how to reduce a matrix equation when you have known essential boundary conditions, okay, which are non-zero. Okay, so if I eliminate these rows and columns, then I get a reduced matrix problems just consisting of this one, this 3 by 3 problem right here, so that I get my, this is my 3 by 3 problem written out. और again I've just substituted, कुछ चीज़ें मैंने ऐसे as general छोड़ी हुई थी, so EI हमें problem में given है for 4 to the power of 6, 10 to the power of 6, sorry, 4 into 10 to the power of 6, and then P is also P is also given in the problem, noting कि जो हमने strong form derive की थी उसमें P was a transverse load acting upwards. ठीक है, please go back to lecture 7 and take a look at that. इस केस में हमारे पास P is acting downward, so there is a minus right here. It's acting in the minus y direction. So substituting all of that, and then this is a 3 by 3 problem which can be solved from our calculators. So directly using my calculator या फिर MATLAB or other computational software to solve it, I get what all of my θ2, V3 and θ3 unknowns would be. Okay, So they turn out to have these values. और अब इसके बारे में ज़रा let's see what these physically mean. So I'm getting that my theta 2 is a minus 0.0013. Now very important, the thetas, they come out to be in radians. Okay, so I've noted that down. This is, the theta is in radians. Now because it's negative, ठीक है जी, that means that is actually clockwise, क्योंकि हमारी कन्वेंशन हमने upwards पॉजिटिव थी फोर्स के लिए और मोमेंट्स जो थी वो एंटी क्लॉकवाइज पॉजिटिव थी. तो अगर मेरे पास कोई मोमेंट्स एंड रोटेशन, सो इफ़ आई एम गेटिंग ए थीटा विच इज़ माइनस, देन दैट मीन्स कि वो बस क्लॉकवाइज है. ठीक है जी. Similarly, अब deflections हमने upwards positive की थी. So if I'm getting V3 which is a negative, then that means that it is downwards basically. Finally, units की consistency की वजह से this V3 also it's coming out to be in M because I just used standard SI units throughout. ठीक है. As you recall, we had discussed कि ये एक units का हमें खुद the user has to be careful about it because end में तो you just get a matrix equation that you end up solving. ठीक है, with complete disregard for what those physical quantities are. तो इसलिए वो जो यूनिट्स हैं, आई ऑलवेज रिकमेंड टू यू कि बस स्टैंडर्ड एसआई यूनिट्स में ही हमेशा रहें ताकि आपके जो रिजल्ट्स हैं वो भी यू नो कि वो एसआई यूनिट्स में ही हैं. ओके. फाइनली इसी तरह ये थीटा 3 का भी वही फिजिकल मीनिंग हम निकाल सकते हैं, जिस नोटिंग के ये थीटा 2 वाज द रोटेशन एट नोड 2, सो दिस इज द रोटेशन एट द मिड पॉइंट ऑफ द बीम, whereas V3 is the deflection at the tip and theta 3 is the rotation at the tip right here. ठीक है, so इसकी कोई deformed shape would become something like this, I'm guessing. तो वो थीटा 2 और V3 जो है ना हमें इस तरह पता चल जाएंगे. ये बहुत ही बुरी बनाई है बट यू गेट द आइडिया. से इट्स समथिंग, ओ बहुत ही, इट्स वेरी डिफिकल्ट टू ड्रॉ विद जस्ट द टच पैड. Okay, so that's for all of my that's for my essential field. So I then know what my deflections and rotations are at each of the nodal positions, and if I want to find it anywhere in between the nodes, then I need to use my shape functions for interpolation, as you all know how to do. Okay, ठीक है, वो मत भूलिएगा, ये सिर्फ नोड्स की वैल्यूज़ हैं, दरमियान में हमें इंटरपोलेट करना होगा यूजिंग द शेप फंक्शंस. परफेक्ट. सो लेट्स देन मूव ऑन टू कि ये तो हमारे पास हमारी एसेंशियल वेरिएबल आ गया सारा, लेकिन व्हाट अबाउट आर अननोन अप्लाइड unknown support reactions, right? So support reactions find करने के लिए I go back to my global matrix problem and then I substitute these values for theta 2, v2, v3, theta 3 that I've just found, and then solve it again to find then q1, m1, q2. Straightforward. Okay, अब इसको मैं solve करूँगी तो I will get what my q1, m1, q2 are. And this time around, इनका physical meaning क्या है? Again, because I was in SI units, I get all of my force and moments in SI units. Newton में force, Newton meter में moment. But for Q1, which is the reaction force at node 1, I'm getting a minus 250. So again, unki sign convention is upwards positive and anti-clockwise positive. So agar minus aa rahi hai, so that means that support reaction is acting downwards. Agar M1 minus aa raha hai, then that means that it's just the moment at the node 1 acting clockwise because it's negative, and then Q2 positive hai, so that's an upwards acting reaction force. Okay, so overall meri problem ko I can write it out just like so. If I'm just looking at the beam, these are my reaction force at node 2, and then my reaction force and reaction moment at node 1, drawn out in the correct physical orientations, right? So Q1 was downwards and M1 was clockwise. That's what those minuses are representing. Okay, so basically we've managed to find everything that we needed. We know now the deflection, the rotation at all of the nodes, and we know the reaction forces which are being applied by the support. Okay, so that's basically it. इसके अलावा हमें कोई भी चीज़ find करनी हो, we can use interpolation. We can use interpolation for the deflections, and then अगर हमें स्ट्रेसेस फाइंड करने हो तो हम उन डिफ्लेक्शन से स्ट्रेन्स फाइंड करेंगे, उन स्ट्रेन्स से स्ट्रेसेस फाइंड करेंगे एज बिफोर. वो सारा कुछ वैसे का वैसा ही रहता है, because that's just coming from solid mechanics, continuum mechanics. Okay, great. So that's the end of this lecture. I do have two examples that I'd recommend कि आप करें. So TED and Blitzko के अंदर से chapter 10 में 10.1 and 10.7a, please, you can do, or go through this example in your own time and solve it completely yourself as well. Okay, so and then we'll have a live discussion on Thursday 5 to 8 p.m. So inshallah I'll see you then. Okay, Hafiz.